Okay, so yesterday we kind of reviewed, really, the work energy theorem from Science 10. Okay, and work energy theorem says that work occurs anytime there's a change in what kind of energy? Mechanical, which means there could be a change in potential, kinetic, or both. Okay, so we're dealing with those situations, which means that this can expand out, and today we're going to work on some problems where this will expand out considerably. All right. If I want to calculate the change in mechanical energy, that means I take my final mechanical energy and I subtract my initial mechanical energy. How do I calculate mechanical energy?
It's your final kinetic energy plus your final potential energy. Subtract your initial potential and your initial kinetic.
Right. If I want to calculate mechanical energy, I have to add together the potential and kinetic at that point. So in this case here, for final, I would write my kinetic final plus my potential final. That would calculate my final mechanical energy. And then over here, I would have my initial kinetic plus my initial potential. So all I'm doing is taking the energy I have at the end in total and subtracting the energy I had in total at the beginning to get the change. See how much the energy changed during that operation. Right? The reason that energy changes is because work was done. And to do work, I have to exert a force through a distance. All right, there's one more expansion that can occur here. Okay, and that would be that I actually put in the formulas for these forms of energy. So the maximum amount that this can go out, okay, is this. I would have 1/2 mvf squared plus m times g times hf. So that's my final mechanical energy there. Okay, minus my initial kinetic energy plus my initial potential energy. Now, those don't have to be in brackets. I just enclose them in brackets so that you can see where everything is and keep the initial and final separate. Truly, those are not in brackets, okay, when this is done. All right, everyone follow me there? Okay. So, a question could say, like, here's your values at the beginning and at the end, and here was the force exerted, calculate the distance over which the force was exerted. Or here's all your values, and here's the distance, calculate the force. Or it gives you force and distance and all but one of these values and asks you what was the initial height of the object or what was the final speed of the object, and you would have to manipulate and isolate and solve. Very much like what you did with law of conservation of energy problems last year. Okay, it's very much like that. It's a lot of stuff that's got to get moved around, but it's just algebra in the end. Okay. All right, so yesterday we finished off and we were looking at 2 and 3. Okay, and what we had was basically an elevator question. This mass was being lifted. Right? They told us that it was 9 kilograms and that there was an upward force of 150 newtons acting on it. Okay? And it acted on it over a height of 5 meters. So the first thing it asked us to do is calculate the work done. And we said, well, we have the force and we have the distance. So the easiest way to calculate work was to not do the whole change in energy thing because, well, we didn't need to. We had those two numbers. All right, so we just went 150 times 5, and we got 750 joules worth of work. All right. The follow-up to that was, what was the change in the gravitational potential energy? Right, so if I want to find change in anything, I take my final and I subtract my initial. Everyone okay with that? Since they don't tell us what the initial height is, but they tell us it was lifted to a height of 5 meters, what do I assume the initial height was? Right. So what does that mean my initial potential energy was? Right. So I can just cancel that off. Okay? If I use kind of, if I talk it through, which is, you've seen me and heard me do that, it sounds like I'm talking to myself, but I'm talking through the problem, I get to find out these little shortcuts, really. Okay? So the change in potential energy is going to equal my final potential energy because I started with none. Okay? So all I have to do then is go m times g times h final. All right, so that'll be 9 kilograms times 9.81, because we have to assume that this is happening on Earth. Okay? Times a height of 5 meters. And when we did that, we got, I think, 441 joules. Okay. How much work was done? $750 joules. So we did 750 joules worth of work, but only 441 of it was used to change the potential energy. What was the rest used to change? The kinetic energy. These are the only two options. Okay? Either it did work against a non-conservative force, or it changed the kinetic energy of the object. Since no non-conservative forces were mentioned here, we have to say that all the rest of it went into changing the kinetic energy, and that's how we solve part C. Right? We know we did 750 joules worth of work, or changed the mechanical energy by this much. Okay? So that means, since mechanical energy is EP plus EK, if I subtract that 441, that'll leave me with the kinetic energy that's left over, okay? And that's going to be 309 joules. Okay, now, that's as far, we got like talking about number 3, but I rushed it because class was about to end. Right? So now I kind of want to illustrate the importance of question number 3 and how net force relates to changes in kinetic energy. Right? So number 3 says, draw a free body diagram for the forces acting on the mass in question number 2. Okay, so our 9 kilogram mass, and I kind of had this drawn before, I just didn't have the rest of it in there. Okay, this was 150 newtons. What's acting down on the mass? Gravity. Okay, and it's going to be 88.29?
Yep.
Okay, so all I did was go 9 times 9.81. Okay, so calculated the force of gravity. Is there a net force here? Okay, so what do net forces do to objects? They make them what? They make them accelerate. Okay, if an object accelerates, that means its velocity and speed are changing. Agreed? Okay, what type of energy relates to speed? Kinetic. So if the speed is changing, so is the kinetic energy. All right, if I had only used 88.29 newtons worth of force upwards, would I have changed the kinetic energy of this box? Would I have changed the potential energy of this box? Possibly. Okay? If I exert that much force upwards and there's that much force downwards, either it doesn't move or it moves at a constant velocity, which would allow me to change the potential energy. If I lift it at a constant velocity, I'm changing its potential, but not its kinetic. Okay? But in this case, there's way more than 88.29 newtons. And so there's a result, there's a net force, and there's an acceleration, and there's thus a change in kinetic energy as well. Okay? So if there's no net force, there's either no change in energy or there's only a change in potential energy. You'll have to get that from the context of the question. Okay? In this case, it says it was lifted, so we know there was. Okay? But in this case, there is a net force. That means that either just the kinetic energy is changing or both are changing. Okay? If there's no net force, either neither are changing or only potential is. All right, so that's kind of illustrated by what they ask us to do here. So calculate the net force acting on the mass. All right, well, 150 minus 88.29 is going to be 61.7?
Yep.
Okay, so there's my F net. Okay, calculate the work done on the mass by the net force. How do I calculate work if I got net force and distance? Force times distance. Okay, so if I go work equals F net times D, that's going to be 61.7 times 5, which which comes up to 309 joules. Okay, so when there's a net force, the work done by that net force changes the kinetic energy. Okay, so if there's a net force, the work it does will be equal to the change in the kinetic energy of the oscillator. Okay, assuming there's no non-conservative forces, like friction or something like that. Okay? All right, everybody okay with that idea? I want you guys to write this one down and give it a try. Okay, it's like one we did yesterday. So a 1,500 kilogram car is pushed down a 15-meter long ramp by a force of 450 newtons. At the starting point, the car is moving at 1.2 meters per second and is 3 meters above the bottom of the ramp. Assuming there is no friction, what speed will the car be going at the bottom of the ramp? Okay, there are two ways to solve this: the short way and the long way. I suggest the work is a change in mechanical energy short way, but it's perfectly valid to solve it the Newton's second law long way. Okay, so if we're just setting this thing up, okay, we know that this side of the ramp is 15 meters long. We know that this thing starts at the top of the ramp and is 1,500 kilograms, and the top of the ramp is 3.0 meters above the bottom of the ramp, and that it is moving at 1.2 meters per second, and that when it gets down here, okay, we are looking for its final speed. We also know that a force of 450 newtons, an applied force of 450 newtons, was used to help it down the ramp. Okay, because if it was a frictionless ramp, would it have gone down the ramp on its own anyway? Yes, it would have. So it was helped down the ramp, okay, with an additional 450 newtons worth of force. All right, so what we're looking at here is that yes, work was done, and the mechanical energy of the box did in fact change. Right? It's going to be going faster at the bottom because of the push than it would be if it just slid. Okay? So we got to do our work energy theorem thing here and figure out what that final speed would be based on the types and amount of energy at the top, types and amount of energy at the bottom. Okay? All right, give you a few more minutes there. So first thing I want to do is kind of do what I always do, talk to myself while I talk this through. Okay? So the first thing I want to look at is, this is an inclined plane and it's frictionless. If I did nothing, if that 450 newtons of applied force weren't there, the potential energy at the top would turn into what at the bottom? Kinetic. It would just slide down the ramp. Okay? And that's work done by gravity. That was going to happen regardless of what we did here. Okay? But in addition to that, there's work being done by the 450 newtons worth of force over a 15-meter long ramp. Okay? So what I want to do is set up my work energy theorem and say that work is a change in mechanical energy. Okay? I'm going to start out small, and I'm going to expand this thing out. All right? So that work can be calculated by going force times distance. I know the force, it's 450. I know the distance, it's 15. So I'm good there. I've got those two numbers. Okay? That is going to change the mechanical energy, so that means my final kinetic plus my final potential minus my initial kinetic plus my initial potential. are any of those energies 0?
Your, final potential.
Right. My final potential is 0 because where am I at the end of this? Right, I'm at the bottom of the ramp where my height is 0, thus I have no final potential energy. So I just found myself a shortcut by talking to myself, or you, whichever. Okay? So now I can expand this out even a little bit further and say, all right, I want to isolate one of these forms of energy. Okay? What I'm looking for is my final speed. Which one of these terms, EK final, EK initial, or EP initial, is my final speed going to be part of? EK final. So before I put in a whole bunch of formulas and make this like a total rat's nest of numbers and letters, okay, I want to isolate that thing, and then I'll expand it out some more. Right? So what I'm doing then is I'm going to add the initial mechanical energy to the work. Okay, does everyone follow what I'm doing there? Okay, I'm just taking this whole thing here and bringing it over here. So what I'll have is that my change in energy plus my initial energy equals my final energy. Okay, when I say that out loud, that makes sense. Okay, work is a change in energy, and if I add it to the energy I had at the beginning, it should tell me the energy I have at the end. Everyone okay with that logic? All right. So now, I'm looking for something that's part of EKF. I gotta expand this out again. So I'll have force times distance plus 1/2 times mass times initial speed squared plus mass times gravity times my initial height equals 1/2 times mass times my final speed squared. Now the term or item that I'm actually looking for is on the board. Tegan, question?
Can you say though that like they're not truly in brackets, so therefore it should be your force times distance plus EKI, and then subtract your your initial potential energy.
Okay, I see what you're saying. They're not truly in brackets. Okay, but up here, when I did this, it was mechanical energy final minus mechanical energy initial. So I subtracted that.
Yeah, which I know you get a positive, but if you look at it like.
No, I know what you're saying,
as
and you're right.
EKI and EPI, they're kind of different.
Right, but I brought them over together
So
as this term, so that stays an add.
Okay.
Yeah, okay, I get what you're saying. I worded it poorly, so I'll own that. I worded that poorly. Okay, so they are they are in brackets, let's say.
Attached,
Yeah,
basically.
they are attached, exactly, yeah. All right, so now I'm looking for VF, and now I can isolate it because it's on the board. Okay, so I'm going to divide both sides by 1/2 of M. Does it cancel? No. I got adding and subtracting up top. It doesn't go away. Okay, it doesn't cancel. All right, and that solves for VF squared. What do I want? VF, so what do I have to do to the other side? Right. Okay, so there's some, decent algebra there for sure. Okay, now I gotta plug in my numbers. So that's gonna look like this. 450 newtons times 15 meters, so the work I did, plus the initial kinetic energy, so 1/2 times, it was 1500, right? Times 1.2 squared, so there's my initial kinetic energy, plus 1500 times 9.81 times 3 meters, that was our initial height. Right, divided by 1/2 times 1500. All square rooted, that will get me VF. Okay. Sorry, I forgot to start the calculator, so you gotta wait a minute for the hamster wheel to start spinning.
The way I did it is I separated it into different steps, cause a value?
for your EP?
Yeah.
That's okay. You're doing the same thing I did.
Okay, yeah,
just in
because
a
I did the
different
same
order.
thing, it's just like a little bit.
Little different order. Yeah, that's fine. You found what the numbers were and then moved the numbers.
Yeah,
That's fine.
exactly.
That's totally fine. Yep. Okay, so when I'm plugging this in, I'll have my square root symbol, and then I'll have on the top 450 times 15 plus 0.5 times 1500 times 1.2 squared plus 1500 times 9.81 times 3 divided by 750, half of 1500. Okay, so at the bottom of the ramp, this thing is moving at 8.3 meters per second. Okay, does that fit? Should it be going faster? Should be going faster than 1.2 for sure. I mean, it would go faster even if I didn't push it, but if I didn't push it, it wouldn't be going this fast. It'd be going a little slower than this. Okay, so all I did was say, there's work being done, the work is changing the energy, okay? I just had to calculate what was that change in energy, add it to my initial energy, so I could find my final, and then find out something about my final energy from there. Okay, question?
I just, because I added these two together, so that would have been. The 1.2?
Right, it's E squared.
Oh, so that's literally the only thing that messed up my
Yep.
test.
Okay, everyone all right with that? Okay, that's a pretty typical physics 20 work energy theorem problem. Now, there was a second way to do this problem. Okay, and I'm just going to kind of walk you through it here. Okay, so if I put that diagram back on there, this side's 15 meters, and this is 1,500 kilograms. Okay, this is 3.0 meters, and there's 450 newtons worth of force acting down. F parallel is acting down. Okay, I don't know what theta is, right? Could I calculate the final speed using Newton's second law? The answer is I could, but I don't like doing it that way because I have to do a lot more calculating. Okay, there's a lot more steps. In this, it all still came down to really one step. I did the change in energy and I used it to find VF. Okay, in this, the first thing I have to do is find theta. Right? So I have to calculate what theta is. Then I could use theta to set up the triangle that we always use for inclined planes. Okay, so once I found theta, I could put theta in here. Then I'd have to calculate FG. And then I'd have to use FG and the theta I calculated to calculate F parallel. Then I would use F parallel and the length of the ramp to calculate the work done by gravity in taking a box down the ramp. And then I would take the 450 newtons and multiply it by 15 to calculate the amount of work done by the box on the way down the ramp. Okay? Or, then I would go back to work energy theorem. Or, I could calculate the net force by adding these two forces together. Okay? And then I could calculate the acceleration. And then I could use the acceleration to calculate the final speed of the box. Is that a lot of steps?
Yes.
It is. And while each step isn't really complex on its own, if I forget one, I'm screwed. Or if I make a calculation error on any one of the many, many steps, I get it wrong. Okay? Whereas with work energy theorem, I just have one formula, I'm finding one thing and doing one operation. I know it seemed like more than that when we were doing it, but in the end it was one work energy theorem operation as opposed to 7 or 8 separate calculations. Okay, try this one. Similar question, still work energy theorem. So we got a large crate whose mass is 200 kilograms rolling along a conveyor. the conveyor uses gravity by being angled 15 degrees below the horizontal. That means the bottom of the ramp is angled 15 degrees above the horizontal, by the way. Okay, to allow the crates to roll down the rollers. The crates are moving at 0.75 meters per second at the top of the conveyor and accelerate to the bottom, which is 2.5 meters below the top, vertically. Okay? There is a frictional force of 150 newtons along the length of the conveyor. Is friction going to make it go faster or slower? Right, it's going to steal energy. So this work is going to be positive or negative? Negative. That means I'm going to have less energy at the bottom than I have at the top. Okay, so that's something we have to recognize before we even start the question. Okay? At what speed do the crates leave the conveyor? Answer is there, so you'll know if you get it right. Okay? So I want you guys to set that one up. It's very similar to the last one. The only difference is the last one, the work was positive. We were helping it down the ramp. Now the work is negative. Okay? It's taking energy away. All right. Okay, let's just look at the setup for this one here, guys. Okay, so we've got 15 degrees, okay, right here, and we know that it's 200 kilograms. Okay, we know that the crates are moving at 0.75 meters per second at the top, and we know that they are 2.5 meters above the bottom of the ramp. Okay, and we know that there is a frictional force of 150 newtons, okay, along the length of the conveyor. Okay, so that would be a negative force or up the ramp. So what do I need to calculate right off the bat here? Yeah, I need to know the length of the conveyor, because that will tell me the distance over which this force does work. Can I calculate it since I know the opposite side and the angle? Yes, okay, that's the first thing I gotta do is find the length of the ramp, okay, and that's simply gonna be 2.5 meters divided by the sine of 15 degrees, okay, that will get me the hypotenuse of that triangle, and I'll leave it there and have you guys try it some more. Okay, so we're looking at 9.66 meters as the length of the conveyor. Okay, so, sorry,
For the force, would it be the force of friction plus the force of gravity?
don't solve it with forces. Solve it with change in energy. This is the only force you're gonna need in this, because it's the force that's making sure that gravity isn't turned into kinetic energy, that gravitational potential isn't turned into all kinetic. Some of it will be. Okay, so don't solve for the force of gravity, you don't need it. If you do it that way, you're doing it the Newton's second law way. It's gonna take you way longer. Okay, let's talk this one through. So, the only reason that the energy at the top of the ramp and the energy at the bottom of the ramp aren't equal is because of what? Is because of friction. Work is done against the force of friction, or by the force of friction, that is reducing the amount of energy at the bottom. Everybody with me there? Okay, so I'm gonna set up, okay, work energy theorem. So this is the second calculation, because I actually had to calculate the length of the ramp in this one. Okay, so I'm gonna say, all right, work is a change in mechanical energy, same as it always is. Okay, that's gonna mean the force of friction, because it's the force doing the work, multiplied by distance, equals, okay, my mechanical energy final minus my mechanical energy initial. What I'm looking for is part of the final mechanical energy, because it's the bottom of the ramp, okay, at the end. So what should I do right now with that initial mechanical energy?
right up into potential and kinetic.
Before I do that, this is what we talked about on the last one where I said I was wrong, and I'm trying to correct my mistake.
Oh, split. Move it as a whole.
Right, move it as a whole. Right now I'm subtracting it, so what do I do to move it over here?
Add it.
Add it, okay. So, I'm gonna have the force of friction times distance plus my initial mechanical energy equals my final mechanical energy. Now I'm gonna expand that out, okay? And I'm gonna say, all right, whoops, that's supposed to be force of friction. Okay, force of friction times distance plus 1/2 mvi squared plus mghi equals 1/2 mvf squared. Why did I not put an mghf squared there?
Because it's zero.
Or sorry, because it's not squared and because it's 0, okay? So, both reasons. So it's 0, I'm not even including it. I'm trying to solve for VF. So all I do is take the 1/2 and I divide it with m over to the other side, and then I square root. So really, the algebra is exactly the same as the last question. What's different is that I have to recognize the force of friction is not helping, it's hindering. Okay, which means I need to make it negative. All right, so when I plug in my numbers, I'm going to have, what was it, 150?
There's
150? Yeah. Okay, so 150 negative times the 9.66, is that what it was? Yeah, 9.66 meters, okay, plus 1/2 times 200 times 0.75 squared, so that's my initial kinetic energy, plus 200 times 9.81 times 2.5 meters, because that was the height initial, divided by 1/2 times 200. All right, so in the end, when I do this, once again, it's 2 calculations. I calculated the length of the ramp, and I did a work energy theorem calculation, which involved some algebra, I'll give you that, okay? But in the end, it was still 1 calculation on its own. All right, so I'm gonna have the square root of, and then I'm gonna put the top in brackets, so that'll be negative 150 times that number. Okay, plus 0.5 times 200 times 0.75 squared, plus 200 times 9.81 times 2.5, end those brackets, and divide by 100, because that's half of 200, close up the whole thing, 5.9 meters per second at the bottom of the ramp. Okay? All right, was there another way to do this? Yes, there was another way to do this. Okay, if I started this out as a Newton's second law problem, okay, I would have only changed that I would calculate, that I would draw FF this way, F parallel this way, and start my calculating, because now I got a whole bunch of things I've got to calculate. Okay, I've got to calculate FG. Then I've got to calculate F parallel. Then I've got to calculate F net. Then I've got to calculate acceleration. Then I've got to calculate final velocity using acceleration, initial velocity, and distance. And I got to use the right distance. That's what I see people screw up on that one, is using 2.5 instead of 15 or 9.66 or whatever it is. Okay, so that's a lot more calculating. It's 1, 2, 3, 4, 5 calculations. Okay, I don't need that many. I can do it in 2. Okay, everybody with me there? Would it be equally valid to do it that way? Totally would, and you'd get 5.9 if you didn't screw up any of the 5 calculations required to get there. Okay, you'd get 5.9 meters per second, but it would take you longer. Okay, are we kind of seeing how these are all kind of similar? Okay, so once we learn the pattern, it's just like it was in Science 10, it's a pattern. Okay? If I can recognize the pattern that is, okay, work's a change in energy, what's doing the work, where's the change in energy, all right, and then just set it up and manipulate, it really ends up just being algebra, as long as I can talk through the problem. Okay? So I understand this one needs to be negative, or this one's the one I'm looking for, or whatever. All right? So I know you might be a little sheepish about talking through the problem on a unit exam, you know, when it's really quiet and people are listening and you'd be giving away the answers, so talk it in your head. Okay? Use the voice inside your head. Unless it says to do bad things. Okay? All right. Okay, so did we do the Raiders of the Lost Ark thing before? No. Okay, we got it. So when he triggers the rock, okay, it is has a mass of 400 kilograms. So sorry, we're looking for the height that it would have had to drop from. Okay, so when he triggered it and then he looked back like this, it was way up above him. Right? And then he started running, and it rolled down that incline and sealed shut the temple. Okay? So what we want to look at is what height would it had to have been dropped from if it rolled for 30 meters against a frictional force of 800 newtons and was moving at 4.5 meters per second when it sealed shut the temple. Okay? So basically, at the bottom of the ramp, because this is really all this is, it was moving at 4.5 meters per second. Okay, and it rolled a distance of 30 meters. All right, so really, it's just an inclined plane like we've been dealing with. It's just this time, we know VF. All the other ones, we've been asked to find VF. Okay, so we know VF is 4.5. What we don't know is the initial height. What was the initial speed? 0. Right, he triggered it and then it started moving. Okay, so we also know that. So this one's actually easier than the last one. Right, and obviously, sorry, we know that this is 30 meters. It's 400 kilograms, and friction is 800 newtons. All right, I'll give you a few minutes on that one. So the only reason that the energy isn't the same between the point that the rock is released and the point where it smashes into the opening of the temple is friction. So the force of friction is what's causing the change in energy. In other words, it's the force of friction that's doing all the work. Okay, so we start out, work's a change in mechanical energy. So that's going to mean the force of friction times the distance, and I have both of those numbers, is going to equal my final mechanical energy minus my initial mechanical energy. I'm looking for something that's part of the initial this time. All right, so since I don't want initial to be negative, I'm going to bring it over here and I'm going to subtract the work. Okay, so what I'm going to have is my initial mechanical is going to equal my final minus the work. Oh, sorry, yeah, minus the work. Okay, everyone all right with that? Because if I take my final and subtract the work, I should have what I started with. Everyone okay with that logic? All right. So now I'm going to have a look at my types of energy. When this thing starts at the initial point, it only has what? It only has potential energy, because it's not moving. We wrote up there that VI is 0. So that means I can write right here M times G times H initial. Okay? And at the end, it only has kinetic. That's what makes this question a little bit easier. Okay? Is that there's only those two kinds of energy minus the work. All right? We'll finish that one up tomorrow. We are going to be doing a lab tomorrow on conversions of energy.
Ministry, please go to the band room. Just a reminder for music ministry.